Part four here for physics, week five. We left off talking about black holes, how it's this combination or it's this battle between nuclear fusion pushing out and gravity pulling in. Eventually, though, we said we run out of fuel. And if you run out of fuel, then gravity ends up taking over. And if it pushes past that there is the electron force holding the outer edges of the atoms, it's enough to hold it. Okay, then it still has a remnant. But if gravity is more stronger than that, it eventually goes past those electrons, and then it's the two nucleuses that are touching each other. Those positive forces is enough to stop the inward pull of gravity. That becomes a neutron star, one of the most dense objects we actually have in the universe. But if we figure larger than three solar masses, so three times the size of our sun, that even the nucleus banging into each other is not enough to stop the inward pull of gravity. So it implodes in on itself, which becomes a black hole. There's more, and you can look up stuff online. It gets into a lot of big stuff with black holes. Just know it is a form of, we get into it is gravity and gravitational interactions that we were talking about form things like the tides, the black holes, your weight on Earth. Those are all gravitational interactions. Well, the last part of this section is going to deal with satellites and satellite motion. Remember we talked about Newton said if you were to shoot a cannon at the top of a mountain, it would go all the way around. Well, that would be a perfect circular orbit as it goes around. What he was able to figure out is that an object falls 5 meters for each second. So if you look at it, and there's the curvature of the Earth that starts to take place, that if we want it to go all the way around the Earth instead of hitting it and running into it, you would have to go a distance of 8,000 meters for it to be able to drop that 5 meters and not hit the Earth. So what does that mean? In order to full circular orbit, you'd have to go 8 kilometers per second in order for it not to ever, because of projectile motion, come down and hit the Earth. The problem with that is once you get going 8 kilometers per second, the air molecules slow you down. So satellites that orbit the Earth have to go up at least 150 kilometers above the Earth in order to get out of the way of the air molecules. You have very little air molecules at that altitude, so it's able to keep going and not slow down, because if it slows down, it's going to eventually crash into the Earth. But if we look at circular orbits, talk about the circular motion as it goes around. You have a tangential velocity, you have gravity. It's the force, it's that centripetal force that's causing it to come in. The amount of time it takes, I think we talked about this with circular motion last week, the amount of time it takes to make one complete revolution is called a period. For Earth, for satellites that are close to Earth's surface, is about 90 minutes for it to go all the way around at that speed. And it gets into this section. You can look through the whole PowerPoint and how long it takes the moon, because the farther you go away and the less gravity there is, gravitational pull, it's not going to 1 second. It's not going to be 5 meters. So it's going to change everything. And it becomes a lot of math that I'm not going to have you guys get into. But know that if it's a circular orbit, basically you stay the same speed all the way around. If it's an elliptical orbit, you start off going, you lose speed as you start to go, and then you speed up as you come back. So let's look at one as you're being launched away from the Earth at a faster speed than that 8 kilometers per second. You don't fall exactly with the curvature of the Earth. You fall a little bit more. But as you slow down, you get wrapped back into Earth's orbit or the planet's orbit, and you come back. And that creates an elliptical orbit, where you would be going slower up here because you're farther away from gravity. You'd be going faster down here as you go, but it would go slow, and then you would go faster as you go around. So you wouldn't have the same speed all the way around, which means you also wouldn't have the same potential and kinetic energy. So basically, elliptical orbits is the difference between two foci, right? If you're doing geometry, this is the focus of one. And if we look at the Earth and we do it for low speeds, the focus ends up being the center of the Earth. So as it goes around, if it didn't hit the Earth, it would come back. And this would be the slow part by the Earth. If you're going farther away from the Earth, the faster part's going to be away.